My talk on multi-scale testing and modeling of cement-based materials. I borrowed several slides for my colleagues, Branko, Henk, Nana, and also our PhD students, Hongzi, Stefan, Yarding, Chen, and maybe more that I forgot now, but thanks to them for allowing me to show their slides. Well, you can use models to do predictions, and sometimes you compare them with experimental data, and those things don't always agree with each other. And then, of course, the modeler that does the modeling, he will always blame the experimental guy. He will always say that the experiments that this experimental guy is doing are wrong. And of course, the experimental guy will always blame the modeler that the model predicts rubbish. So that's always the case. So that's why we decided in Delft to do both, because then we can blame ourselves if something goes wrong, and maybe we can improve things, and that we collaborate with the people that do both of the things. So that's the idea, that we always do modeling and testing and compare results. Of course, we have a big challenge in the concrete world. We have to also contribute to the overall all of the world development of reducing CO2. So this is a picture I took in 2019. You see in Norway, in Trondheim, where they had a conference on reducing CO2. And you see how much we have to do in the coming 40 or 30 years to 2050, what the goal is of the reduction of CO2. And of course, from the construction world, we have to contribute to this. What can we do then from concrete? How can concrete contribute to this to reduce the CO2? Of course, we can go to green binders. We can use recycled materials, recycled aggregates, but also maybe recycle the binder. We can, of course, reuse concrete elements or reuse concrete structures to use them again, maybe in different structures, these elements, but that's towards a circular economy, reusing things, not throw it away when it's at the end of the lifetime. But very important, we can also use less materials. And using less materials, then of course we can think of 3D printing. We heard the excellent presentation of Victor before the break. That's something we can do. We can work towards optimized material structures, so that the structures or the materials distribute the loads in a more optimized way, that you only use material where it is needed. And we can, of course, use self-healing materials. Self-healing materials, they repair themselves if you have damage, and they will last longer. So that are things we can think of if we want to contribute to the reduction of CO2. And of course, modeling can help to optimize these things. So we combine modeling and experiments, so both of them can be used to optimize the materials that we reduce CO2. So what are the topics for today, for this talk? 3 topics: multi-scale modeling and testing. That's the main part. Then I will tell something about self-healing concrete that we are doing in Delft. And I will also focus a little bit on 3D printing at different scales. At the end of each topic, maybe there's time for a few questions. Maybe you can also use the chat to put those questions. I can keep an eye on the chat, so in between we can answer some questions on the different topics. Maybe that's good, because when they asked me if I would like to present our work at this workshop, they asked me how much time would you like to have, and I said, oh, maybe 90 minutes, 1.5 hours, because that's a usual lecture in Delft. But there's always a break of 15 minutes, so I didn't communicate that. So now I have to talk for 90 minutes. So maybe to have some questions in between would be good. But I will start with the multi-scale modeling and testing. And so what you should remember from this is how to measure input parameters for your modeling. That's what I will focus on. How to validate models. If you make a model, if you do multi-scale modeling, how can you validate them, and how you do the upscaling. At least that would be good if you learn that for my presentation today. Of course, what I tell is not the only way to solve these problems. This is just examples of what we do for the models that we use in Delft. And of course, there are a lot of different methods available that you can use, but these are just examples, and you can learn from it and maybe use it in your own research. So if you do multi-scale modeling, you can go all the way from the nanoscale of the CSA shell that is produced in concrete up to the macro scale where you really have big structures where you have damage. And in between, you go to micro and meso, where you go to cement particles, include aggregates, include cracking, and then you go to real damage. Of course, we can start at the nanoscale, at the very small scale, but we never build on this scale. We always build on the macro scale, and that's where we get the damage. So we have to go all the way to see what consequences that has. But the building blocks are, of course, on the nanoscale. So maybe it's good to start very small, nano or micro, and try to predict what is going on the large scale. But for that, you have to pass several scales and connect them to each other, and also get your input parameters on the different scales, and also do validation on different scales. So I will show some examples how we can do the modeling and how we can optimize that, and how we can use testing experiments to get values for that. Because you need input values, you need to validate your models. Because if you only do modeling, then that's not good, because some people believe in their models, that everything the model predicts is right. But I never do. I always want to see what is happening in the real material, in the real structure, in the real experiment. So you can, for instance, do multi-scale modeling, go from cement paste to mortar to concrete. You can have models to build your cement paste, where you put cement particles in a liquid, and you can simulate what is happening with the hydration, how these cement particles react with the water, how they build up the cement paste around it, how they build up this microstructure. And then you have the building block of concrete. Of course, if you go to mortar, you have to add some particles. You have to add sand particles. And if you go to concrete, you have to add aggregates. And that makes it more complicated, because then you not only have the cement paste, which is the glue of your material, but you also have aggregates and the connection between them. So they are connected with each other. You create an interface there, and you need properties of that. But you can do that with modeling and testing of the material. And you have to determine these local properties of the material, so the properties of the cement paste, of your interface, of your aggregates. And you can do that in different ways. You can do testing of the material, mechanical testing, a small-scale testing of small samples of cement paste. You can do compression, you can do tension, you can do three-point bending, as you see in this image, on a very small sample, and get the properties of your cement paste. That's one way. You can also use CT scanning, because CT scanning can tell you something about the microstructure of the material. If you, for instance, put sand particles in, or if you put fibers in, you can do a scan. You get an image of your structure, because that's also important if you go to modeling, you need the properties of the different components, but you also need the microstructure. How does it look like? What is the shape of your features in your microstructure? That you can get from CT scan. If you model the cement paste, of course, that's also not a homogeneous material. It's also very heterogeneous. You have cement particles and you have the cement stone around it that is formed, the CSH gel that is formed, and you also have to measure properties of that. And one good way to do that is to use nano-indentation. Because nano-indentation, you can indent in the different phases of the material. After you make the material first, you have to polish it very nicely because you have to have a very smooth surface. And then you can do indents with a nano-indenter that you see, for instance, here on this surface, and all these small dots in this image are the indents done with the machine. And then you can measure a curve like this, the load displacement curve. So you push a small needle with a diamond tip inside the material and you unload. And from this curve, you can get a hardness, which is the maximum value that you obtain, divided by the cross section of your indenter at that certain depth. And from this slope, or also in some cases from the slope of the loading curve, you can get the stiffness of the material, the local stiffness of the material at your indent. So you get the hardness and the stiffness, which are then input parameters for modeling. That's a way to go if you want to get the properties of such a cement paste. So that are techniques that can be used to get properties. But you can use different models to do simulations of the materials, to look at mechanical properties or diffusion or temperature rise due to hydration. So you can use finite element tools, but we are used to discrete models, and we developed this lattice type framework already a long time ago, but we are still using it. The principle is that you discretize your material as a network of beam elements. Those beams, for civil engineers, they are easy. They can transfer normal force, shear force, bending moment. That can be a 2D network or a 3D network, as you can see here. All these elements usually are linear elastic and brittle, so they have a certain stiffness, at a certain strength or strain, they will break. And that's the behavior of the material. Of course, for such a network, if you model a material, you have to implement some disorder or some heterogeneity. But that you can do. I will show later how to do that. And then you apply just simple an external force or an internal force or deformation on this network. You can just pull on it, and then you perform a linear elastic analysis, calculate all the stresses in all the beams, and remove one beam following a certain strength or strain criteria. And what you do is you remove the beam with the highest stress compared to its own strength. You relax the displacements and remove the next beam. And that's a procedure, and with that you can simulate crack growth in such a material. So you can, for instance, do a mechanical performance evaluation of such a cement-based cube. This is typical cement-based cube of 100 micrometer. So with cement particles between 10, 20, 30 micrometer each. This is simulated with a tool that we call Hymerstruck, which can generate the structure of the cement paste starting from the cement particles in the liquid, in water. So they react with the water and they start to grow outside, which is the yellow part, and inside, which is the red part. And then, of course, you start with floating cement particles and you end up with a solid microstructure with still porosity inside. Of course, such a cube you can transfer to a digital image, and you can create such a lattice around it. So this is an image made up of these lattice elements from the previous picture, like this, but then a very fine mesh where you have then certain elements inside the cement particles, elements inside the cement paste, the CSH gel, or the CH gel, and then you have also porosity, the blue part. There you just leave the elements out because that has no mechanical strength. So there you just have pores. And then you can study, if you start to pull on this, loaded in tension, what kind of properties do I have? Of course, you can plot that and you can investigate that at different degree of hydrations, because this model of the cement particles, it hydrates in time, it builds up the microstructure in time. So if you do that at a low degree of hydration, you have a lot of porosity still in there. And if you start loading it, you get a lot of micro cracks around your body because it's still very heterogeneous. If the degree of hydration increases, it becomes more homogeneous, and if you crack it, then you get more one crack plane without micro cracks. So it becomes then stronger, but also more brittle because you have less micro cracks. And you can study these features, these behavior of the material versus the degree of hydration. That's one possibility to do this study. But then how do you validate the model? So I said already, you can do non-indentation to get the properties of your individual phases. So you can indent in your unhydrated cement particle, you can indent in the cement paste, get the properties there, use that as input. But that's not the validation, that's getting your input parameters. So to validate, you still have to do a test at each of these scales. So yeah, if you do simulation here, you have to test it. You can upscale to the mortar. You can test the mortar. You go to concrete. You can test the concrete to validate. Of course, on the concrete level, we know how to validate this. We can do a tensile test. We can do a compression test on such a cube. And we get the properties of the composite. So we can do such a test. On mortar, also still possible. We can do compression test or tensile test, get the properties of the mortar, so that we can validate. But on cement paste, it's not that easy because I said this cube that we start with is 100 micrometer. So you have to make samples that are 100 micrometer in size and do a test on that. It took us some time to come up with a method to make them, and we bought a special machine to make our samples. It's actually a very precise dicing saw that they use to dice wafers from the electrical industry, where they make these small chips that they put in your mobile phone. With that, you can very precisely cut samples, which are very thin. Wafers, they are very thin, like a CD, that they cut in small pieces. So what we do is we glue a piece of cement paste on top of a glass plate. Then we cut the cement paste and polish it, that we end up with a thin layer of cement paste on the glass plate, a layer of 100 micrometer. And then we use this diamond saw, this dicing saw, to cut in two directions. And then we end up with small cubes that are left on the glass plate. And those small cubes can be of the size of 100 by 100 by 100 micrometer. And this is the image of these small cubes on the glass plate under the electron microscope. And you see what kind of samples you end up with. So then you have small cubes on the glass plate of cement paste of the size that we want to test. How to test them, because you cannot go to a normal mechanical testing machine. So what we do is we use the nano indenter with, for instance, a BERKOVICH tip, which which is a pyramid that you see here, that you also use for normal indentations. And we can press inside a small cube and split the cube open. So that gives you a value of the capacity of this cube. That still is not a value which is a standard test, but we can do the same with our model. We can have the local properties that we get from the normal indentation, give those properties to the beams, load our cube on the computer also with a BERKOVICH tip that we see here. We split open the cube on the computer and we get a maximum load for this sample. And that maximum load we can compare with the test. And in that way we can do a validation. So we measure the local properties by nano indentation, we put it in the model, then we do on a larger scale a test for validation with the nano indenter loading this cube. We simulate this cube also on the computer and we can compare the maximum load, the outcome of the simulation and the test. In that way we validate our model. So we can load with the BERKOVICH tip, but we can also load with the knife tip that you see here. This is just a knife. We can split the cube, then we have kind of a Brazilian splitting test. Not completely, because we load only at one side and not at two sides, which you do with the Brazilian splitting test. But this is another way of loading it that we can also model. This is a typical result of the loading of such a cube. So this is the cube after the test. So you see we have the initial phase, it's elastic, and then it goes to the peak load. We cannot measure the post-peak behavior that you might expect. Of course, this is cement-based, it's quite brittle, but also the nano indenter, the machine, is not that fast to retract the load and to measure the whole post-peak behavior. So we can go up to the peak and then we have failure like this. Of course, of such a small sample, you also have a lot of scatter. It's very heterogeneous. So here you see results for cubes made with different water-cement ratio, 0.3, 0.4, and 0.5. So what one graph is, this is for instance for 0.3 water-cement ratio. So you see the scatter that we have. You can ask, is this real? I think it's real. We have such a big scatter of cement paste on this level. Of course, also the preparation of the specimens will lead to some errors at the surface, but if we measure cement paste, we should expect such a scatter. But the beauty of this method is that we can do a lot of tests. So you can do, for this series, we did more than 100 tests for each cube. Because it's very simple. You make all these cubes on a glass plate, you put the glass plate in the machine, you set the machine, and it will do the test for you overnight. And in one night, you can easily do a couple of 100 tests. So if you come back to the university the next morning, then you will get all your results. So here you see for the different water-cement ratios, the number of specimens, and this is the strength that we measure. So you might say, well, this is pretty high. So a strength of 22 megapascal for these cubes, and for the 0.5 water-cement ratio, still 18 megapascal. It's quite high, but it's a very small specimen. Keep that in mind, that we have size effect, and we should expect on this level a very high strength. So if we get a high strength on this level and we do multi-scale modeling, you also have to implement in your models this high strength on this level. So because of what I often see is that people do a strength test on a much higher scale and then try to simulate on a small scale and use the properties of the high scale. That's not good. So the size effect is there, and you have to implement in your models these high values if you simulate on a very small scale. So here you see some results of the splitting test of the modeling we did. So put the knife on the cube and you see the crack plane that develops. And of course you get then also loads in there. So here you see also the scatter. We also have in the simulations, of course, if you start with a different microstructure, then you also get a big scatter in your simulated results. And of course, with the model, we can predict the post-peak behavior. And you see already that it is quite brittle, but we can predict that if we start with the microstructure that was simulated from the Heimerstruck model with the cement particles, we can predict such a behavior. Of course, then we can test at different scales. So here you see the small cubes that I just showed that we did with splitting. You can make some bigger cubes in the same procedure of 200 micrometer, but we can also go to cement-based cubes, which are bigger. So this is 40 by 40 millimeter. So we have a huge size range from 1 to 400 to test the size effect of this material. Of course, these big cubes we cannot test anymore with the nano indenter because they are a little bit too big, but we use a normal install machine with a knife to test those. So what do we see then? So if you go from the cubic size from 100 micrometers, so 0.1 millimeter to 40, so we see a huge change in strength. So here we have this 18, and if you go to the biggest one, we only have 1.18 megapascal as a strength in such a splitting test. So you see huge size effect. You also see that the standard deviation here it is much larger than on the large cubes, but that's what we have to deal with. But this is important to know that you have this size effect on the material. You can plot it versus different size effect laws. So you have to be careful because Beppe is probably still watching, and he did his PhD some time ago on size effect. But if you plot them versus different size effect laws that are available, they all match still quite well, I think, in this range that we tested. If you go to much smaller or much larger, then the size effect laws differentiate quite a lot. But in the range that we did the test, we can fit with all models, and what happens here and here, I don't dare to discuss that. So if we can make cubes, we can of course also make beams, because that's same procedure. Put cement base on glass substrate, cut and polish it off that you have a certain thickness. In this case, we went to 400 micrometer. Then you cut with your diamond saw again. In this case, only in one direction. You dissolve the glue from the glass plate, and you can take off this small beam. And of course, you can then load this beam with a knife indenter to do a 3-point bending test. So we did that. I will show you later. But we also put this beam in a special holder. Well, this is a clamping device, which is the inside of a pencil. You just take it out of the pencil, which has a nice clamping device already in there. We can put the micro beam in there and put it inside the CT scanner. So then we can scan this beam at a very high resolution to get the microstructure of the beam. So that's what we did. And what you do if you scan these, you get different grayscales of the different materials, and you can transfer that to your unhydrated cement for a very high grayscale, for the inner and outer product of your reaction products, and to porosity for the ones with a very low grayscale. So for that, you can get your microstructure. So that we did for the different water cement ratios that you see here, 0.3, 0.4, 0.5. And you see, then you have similar microstructures that we had when we started with the Heimerstruck model, where you start modeling spherical cement particles, do the reaction of the cement and the water, and you get formation of your microstructure. So you get similar images then by scanning it, but of course we know that our cement particles are not spherical, but they are irregular of shape. So this is more closer to reality if you do it in this way, if you do it with the scanning and get your microstructure from there. So we scanned the beam, took out some cubes to do some further analysis on. So these cubes that you then have scanned, you can know the intention, you can see how cracks propagate through these microstructures, and you can get the mechanical properties from that. So again, we get the local properties from the nano-indentation on the different faces, and we then simulate the cube, and we can get the strength of the cube. In this case, we have tensile strength 25, 18, and 15, which are close to what we had before, a little bit higher, but a similar ratio that we observed before. I said we can make these beams, we can load them in 3-point bending. So typically they are, in this case, 500 micrometers or half a millimeter each side, a length of 12 millimeter. We made a special support from them, and we can load these with the nano indenter. So we can put them in a nano indenter, observe with a special camera from the side how the nano indenter with a knife tip breaks those small beams. Also here we cannot measure the post-peak behavior, so we can go up to the peak, then it breaks, and it's the end of the test. So here you see some of the tests. So you see the beams failing. This one will also fail. Yeah, you see it failed. So this is what you then see with the camera. We are trying to do digital image correlation also on this, but it's all quite small, but we're going to do that in the future to see what kind of deformations we have in time. But we also did some glass beams to check if the method actually works. Of course, the glass beams, they are much more homogeneous. They all have the same properties. If you just start with a plate of glass, cut it in beams, you can test them, and you see the strength of all of them is almost equal, very small scatter, and it's close, very close to the values that you can find in literature for the glass. So we are sure that this method gives accurate results. Of course, for cement-based beams, we can measure the strength, but the scatter is much larger, and we again see different for different water-cement ratios. And the strength is 20, 15, 11, somewhat lower than the tensile strength that we measured, or the splitting strength. But that's clear because this is a somewhat larger scale. The splitting strength was on cubes from 100 micrometer, and now we have a cross section of 500 micrometer. It's already somewhat larger, so we expect to see differences. And we can actually model then these beams. So this is a tensile test on a small cube. We can model the result. So this is the result that we get from the modeling. So you see we get the post-peak behavior. We can do a multilinear fit of this curve. So the red line with the dots. We implement that multilinear curve for each of the elements in the beam. So they have this behavior as the red curve. And then we can simulate the behavior of the beam. So that way we do the multiscale modeling. So we start on a very small scale with elements of 1 micrometer. And we simulate a 100 micrometer cube. The result of that curve we implement in the elements of the beam, and then we can simulate the beam. So here you see the scatter that we have of all these results. And here you see the curves that we get. You see also in the simulation, the results are very brittle. Although the input of the beam itself was not that brittle. We had some softening. But the results of the beam, you see they are very brittle, and that's also what you saw in the test. They fail in a brittle manner, although we could also not measure it with a nano-indenter to get the post-peak behavior. So here you see the strength results for the different water-cement ratio, the comparison of the modeling and the testing. So they are nicely in the same range. So our method works with the upscaling. So we can get similar values. And that seems very promising. But if we go to mortar, to concrete, we are going to add aggregates. And that makes it more complicated because now we add an interface. So we have the hardened cement paste and the aggregates together and an interface in between them. And we also wanted to test that. So what do we do to test the real interface on this small scale? Because if you are modeling on the small scale, we also have the tests on that small scale. So what we do is we use an aggregate. We cast cement paste on top of it. Of course, we got the aggregate to have a smooth surface. We also polished it, but we also did non-polished aggregates to see the influence of that. So you cast cement paste on an aggregate. You cut with your blade again in two directions. So you have then small pillars on top of an aggregate and an interface in between them. So this is how they look under the electron microscope. So small pillars, 200 micrometer in height, 100 micrometer in cross section, and this is the aggregate. So we cut a little bit into the aggregate. Here you have the one interface. Then we can load with our nano-indenter from the side on these pillars, and then the pillar will break. So that gives you then the strength of the interface of the cement paste connected to aggregate. Of course, that's not a real value that you get. You get the outcome of this test. So you still don't know what the local properties of your interface is, but you do a test to measure an interface, and from that you could fit back what your local property is. What we also did, we scanned these small pillars again in the CT scan, and you can look at the grayscales. So grayscales in the cement paste. This is the aggregate, which is much higher. And you can also see what kind of porosity you then have. So you can transfer this image to this colored image. So you see the unhydrated cement particles, hydration products, the red and the yellow, and the blue one is the porosity inside the sample. And you see that the porosity is higher at the interface. What you also expect, that you have high porosity there because your cement particles are not nicely distributed. You have some more water, so you end up with a higher porosity, which creates this kind of weak interface between aggregates and cement paste. Of course, there are a lot of ways to improve this interface, but just we didn't improve anything. We just tested this as we made the material. Then we can do a test also on the computer of this aggregate with small pillar connected to it, with the heterogeneity that we measured in the CT scan, load this specimen and measure what kind of strength we get at the interface. But we still didn't know what kind of properties to implement in the interface, but that we can then fit. We just put some properties of the interface element, so the connection between the cement paste and the aggregate. We just fit those values that we have a match between the experimental results and the simulated results. So these two are the simulated, these are the experimental curves, that we get the same strength. So we just fit those properties that they match. That way we can obtain the interface properties that we can use them for further upscaling. So now we want to test a mortar sample with some nice sand particles in it, aggregates, but small sand particles. So we have aggregates, the orange or red ones. We have the cement paste, and we have the interface elements. So the cement paste is already on the level of the size of 100 micrometer, something between the aggregates and the elements are quite large, not on the micrometer scale, but a little bit bigger. So what we put in for the cement paste is already a nonlinear behavior, a softening curve that we got from the small scale simulations. So that's this curve. We put that in as property for the cement paste. For the interface, we put the properties that we just measured from our small interface test. These are the properties for the interface. And the aggregates, we just put elastic, they don't break, we said. And the microstructure we also got from, we made the material, we scanned the material in the CT scanner to get the distribution of the aggregates. Then we did this test, loaded this small sample with a notch at two sides in our install machine to get the mechanical properties of this test. And we can do the same on the modeling. And then we see without any fitting anymore, we get almost equal results. Of course, there is scatter, but that's what you expect. But the testing and the modeling, they nicely fall in the same range. So by measuring on a local scale the properties, put them in the model on this scale, we can have a nice fit of the material. So that's the way we try to do multi-scale modeling of cement paste. But of course, we also want to add different features to the material. Here you see that we added also fibers to go to a strain hardening material. You see me a few years back breaking the material. I just wanted to show the deflection, but then of course it broke, because if you deflect it too much, then it will fail. And in this case, we were studying also the influence of phase change materials to it for a special project. So they are shown here and they are mixed in these samples. But you see, if you load them in bending, you get a lot of deflection and you get a lot of small cracks in the material due to these fibers that we put in, these PVA fibers. Of course, this is the strain hardening material that you can get in tangent or in flexure. Of course, this strain hardening behavior changes in time. So in the beginning, you have a lot of deflection, and it gets a little bit less if the material is fully hydrated. But that's the case. We have to live with that. We can look locally in the material. So here we see the phase change materials that were in there, and also the fibers on a local scale that were inside the material. But we also wanted to see how does this fiber bridge the sample. So since we have this special saw, we were able to make very small beams, again of cross section of a few hundred micrometers and this length of 12 millimeter. We got the sample, so you see then the fibers aligned here. These are the phase change materials that were in there. And this one was loaded in 3-point bending to get a crack in there. Of course, I asked the PhD student to make the samples in such a way that the fibers were nicely bridging the material in that direction. But that's not easy to cut it exactly there where a fiber is. So you see fibers are randomly in the material and are not perpendicular to the crack, because that was the idea to make that. But we could still scan the material. So here you see a scan of the crack, where you see the single fibers. You see the phase change materials, and this is actually the crack plane. So we wanted to see how these fibers bridge the crack, and if maybe the fibers slip or the fibers break if you create a crack. But it's not easy to see that on this scale. So we still want to continue with that, because then you can really study on the small scale how the fiber connects with the matrix, how it works, and what kind of properties you also have to put in the material if you do modeling. So that's the next one. If we want to model a fiber material, we can use the same discrete model, the lattice model, and then put discrete fibers in the material as you see here. So the red one is the fiber, the yellow one is the matrix, and we have special interface elements, these dashed lines that connect the fiber to the cement matrix. So we can build a model of that. But of course, these interface elements, or these dashed lines, there you don't know what kind of properties you have to put in. So you can do a pull-out test of a single fiber, pull it out, measure the load that is needed, and you can do the same on the computer. Pull out the fiber, you get a curve of your pull-out behavior, and just fit the properties of this connection from the comparison of the model and the simulation. That's the only way to get the local properties of this interface. I don't know how to measure it in another way. Just fitting it by doing a test on a somewhat larger scale. Then you can put the fibers in your matrix, different amount, different directions, and you can try to simulate the behavior. And what you want to end up with is the last one. That if you put it, you have a strain hardening material and you have multiple crack planes developing in the material. That's also what you see here. If you have the right amount of fibers, the right properties of your fibers and the connections, you can, in the model, you can have a strain hardening material and you get multiple crack planes developing in the material. And if this works, you can start to optimize it, change the properties of your fibers, of your interface, the dimensions of your fibers, the amount of fibers, and see what kind of influence that has on the behavior of your material. So then you can really use your model as a design tool to design your material. One of my colleagues, BERKOVICH, she also used this to simulate shrinkage of these strain hardening materials, to use it as a repair and then study what happens if the material dries out and shrinks. So on the computer, she prepared the old concrete, did some sandblasting on the computer that the aggregates are exposed, cast the repair material on top of it with the fibers in it, expose it to drying, and then simulate the shrinkage of the material and the cracks that develop, doing that with and without fibers, and look at the differences. Of course, it's the same as cracks in nature that you see concrete, mortar, clay. You see these same crack patterns. They just come out of the model if you do these simulations. And of course, if you put fibers in it, then your cracks will be much smaller. You have a different configuration of the cracks. So this is without fibers, this is with fibers. Your cracks are smaller, closely spaced. That are things you can then study. What happens with your material? What is the effect of the fibers? She also scaled it up, this model, to simulate this kind of fracture in beams, so reinforced beams. You could call this a shear crack. I just call it a tensile crack. But if you do the simulation with this, with reinforcement in it, you see if you first have bending, your cracks will start, and then one of these cracks will open up. You can call that a shear crack, but it's just, I would say, because the tensile stresses rotate and your crack propagates to the maximum tensile stress. So then you can study different H/D values, so the height and the distance between the support, to see how these cracks will change. And you can compare that with data from literature, from real tests. You can see similar behavior that you can then observe between the modeling and the testing. And if you look at the maximum capacity of the experimental one and the modeled results, they are quite close. So for the 3 different H/D ratios, only this experimental one I think it stopped too early. The deformation should be much larger as we had in the simulation. So in this case, I would say the test is wrong and the model was right. But of course, we only did the modeling here and we took the test from the literature. So then I can claim that the model was correct. Well, maybe not. So what should you remember from the multiscale modeling part? So the first part of my talk. So how to measure input parameters. I showed you different features, different tests, how to do that on different scales. What is very important that you validate your models. You validate you measure input parameters, put them in a model, and then the result of your model you have to validate with another test. And this validation you have to do at every scale. Because if you do multi-scale modeling, you start at the nanoscale and you go all the way up to the macro scale. You don't test in between values, then you can predict something completely out of scale, out of your real results. So you really have to validate at each scales if you do multi-scale modeling. And I showed you how we do the upscaling, but there are much more techniques to do that I didn't discuss. Questions about this part? I see. Beppe said the material is weak or Erik is very power. What do you mean, Beppe?
Professor, I have a curiosity, not a question.
Okay.
Do you think that the same strategy can be used for other special concrete, such as foamed concrete, including the presence of air bubbles in the model?
Yeah, I think that's the beauty of such model strategy, that you indeed start from the microstructure, put the local mechanical properties in your model that you can measure the local properties, and then simulate the behavior of your composite. And the composite can indeed be anything. It can be with normal aggregates, can be with recycled materials, but it can also be with air bubbles. If you put air bubbles in, then you have a different microstructure, and you can just follow the same procedure to scan your material, put these air bubbles in your microstructure, and do the simulation and see how your material responds to fracture tests. So that's similar, and you can apply that to all different kind of materials where you change the local properties. So that's the beauty. So you can then predict what behavior that material has.
Thank you.